All right, welcome back. In our last explainer, we dove into bit masks, how you can read and write individual bits. Well, today, we're going to make those bits move. And you're about to see how this simple act of sliding ones and zeros around is the secret behind some of the absolute fastest operations a computer can perform.
So let's start with a little bit of a puzzle. How can a CPU possibly multiply or divide a number without ever touching its multiplication or division circuits? I know, it sounds kind of like a magic trick, but the answer is this beautifully elegant principle that's right at the heart of how computers actually work.
And that solution is an operation we call a bit shift. It's one of the most fundamental things a processor can do, and really, it's all about getting a powerful result by just moving data around.
So what exactly is a bit shift? Well, it's pretty much what it sounds like. We take all the ones and zeros that make up a number and we literally just slide them over either to the left or to the right. Think about it in our own decimal system for a second. If you take the number 58 and just add a 0 to the end, you get 580. You just multiplied it by 10. Bit shifting is the exact same principle, just working in base 2.
And as you'd probably guess, this can go in two directions. We can shift to the left, or we can shift to the right. In a lot of programming languages, you'll see these shown with the double angle brackets. And as we're about to see, each direction has its own very specific mathematical superpower.
Now, it's super important to get this. A bit shift isn't some kind of approximation or a sloppy shortcut. Nope. It's a mathematically exact operation. It's predictable, it gives you the correct answer every single time, and that's precisely why it's so critical in high-performance code.
Which brings us to the main event, using these simple shifts to do lightning-fast multiplication and division. This is where that magic trick we talked about really comes to life, and it's why this is such a go-to tool for programmers who are obsessed with performance.
Let's start with shifting to the left. The rule here is incredibly simple and incredibly powerful. Shifting the bits of a number one single position to the left is the exact same thing as multiplying that number by 2. That's it. Just like adding a 0 multiplied our decimal number by 10, this multiplies our binary number by 2.
Let's make this real. We'll start with the number 11. In a simple 4-bit binary, that's written as 1011.
Okay, now let's just shift it left by one spot. Everything slides over, and a 0 gets popped into that empty space on the right. Our new binary number is now 10110. And if you convert that binary number back to our decimal system, you get 22. See? We just multiplied 11 by 2 and we never touched a single piece of multiplication hardware. It's that direct, and yeah, it's that fast.
Okay, so if shifting left is multiplication, it kind of makes sense that shifting right would be division, right? And it is. Shifting the bits one spot to the right is the same as doing an integer division by 2.
Let's stick with our friend, the number 11, which is 1011 in binary.
So this time, we slide everything to the right. The whole pattern moves over one spot, and that rightmost 1 bit, well, it just gets discarded. It falls right off the end, into the void. Our new pattern is 0101.
And the result? The binary 0101 is the decimal number 5. Now, I know what you might be thinking, hold on, 11 divided by 2 is 5.5. And you're right, but this is what we call an integer division. Any remainder just gets dropped. That's a really crucial thing to remember about the right shift. It can be lossy when you're dealing with odd numbers.
But of course, things get a little more interesting, especially when we start working with negative numbers. Turns out, there isn't just one type of right shift. We actually have to make a distinction between a logical shift and an arithmetic shift. A logical right shift is pretty simple. It always fills that new empty space on the left with a 0. But an arithmetic shift is a bit smarter. It looks at the most significant bit. That's the one that tells us if a number is positive or negative, and it copies that bit into the new space. Now, why would it do that? Well, it's absolutely essential to make sure that when you divide a negative number, the answer actually stays negative. So we know what shifts do, but this brings us all the way back to that first question. Why on earth are they so ridiculously fast? And the answer to that lies deep inside the hardware itself.
I mean, think about it this way. Multiplication and division. They need complex, specialized circuits on the chip. They're multi-step processes. A bit shift, on the other hand, is one of the most basic, primitive things a CPU can possibly do. It's almost like flipping a physical switch. It happens right there in the CPU's fastest internal memory.
the registers, usually in a single, predictable clock cycle. It's not a calculation. It's a direct manipulation of the data. This is pure hardware speed.
And let me tell you, this is not just some clever trick for programmers to show off. This raw speed advantage means you will find bit shifts everywhere that performance is absolutely critical.
They are at the very heart of algorithms for hashing data and compressing files. They're used constantly in graphics programming for super fast color and position calculations. Cryptography relies on them to scramble data efficiently, and really, any time you're in a tight loop in a program that has to run millions of times a second, you can bet that a smart compiler or a clever programmer is using bit shifts to squeeze out every last drop of speed.
And all of this really points to what I think is the single most important lesson here. It's a deep truth about writing truly fast software.
See, bit shifting isn't a hack. It's a direct consequence of the physics of how numbers are stored. When you really understand the binary representation of your data, you unlock simpler, more direct, and therefore much, much faster ways to manipulate it. This is where real performance comes from. Not from clever tricks, but from a fundamental understanding of the machine. And we are going to build directly on this idea in our next explainer. We're going to combine what we now know about masks and shifts to solve a classic problem. How do you efficiently count the number of ones in a binary number? That's when bit manipulation stops being just a speed trick and starts becoming an algorithmic superpower.
So the next time you see a multiplication or a division by a power of 2 in some code, just take a second to think about the hardware underneath it all. The fastest way to solve that problem might not be with math, but by simply shifting the data. Thanks for joining us.